1 minute. Okay. Thank you for introduction. The talk of Elena Borisovna was so interesting that it was very difficult to finish it. There was a lot of questions, and you can see that we are scientific relatives with Elena Borisovna Yarovaya, with Professor Yarovaya, and my talk is also devoted to branching random walks. It is called Propagation Front of Branching Random Walk with Periodic Branching Sources. First of all, I would like to thank the organizers for opportunity to have a talk at this remarkable conference dedicated to 85th anniversary of Professor MALYSHEV. I was acquainted with this prominent scientist. He impressed everyone by his energy, enthusiasm, erudition, and wide range of interests. Among his research interests, there were the spectral problems of dynamical systems with an infinite number of particles. For important contribution to mathematical physics, Professor MALYSHEV and Professor Minlos were awarded the State Prize of Russia in 1991. Mathematical models of evolution of a population of particles, genes, individuals, in space and time, propagation of epidemic, spread of fire, and etc. are of a great theoretical interest, and they are important for applications. It is sufficient to mention the classical paper by Kolmogorov, Petrovsky, Piskunov, monographs Hackle, Jaggers, Vatutin, Allen, Kimmel, Axelrod, Britten, Pardue, and others. Recent years, a lot of publications written in the leading scientific centers of Germany, Italy, China, Russia, USA, France, Japan, and other countries are devoted to the models describing the population behavior in space and time with the help of branching random walks. You see some books devoted to branching random walks here. Such stochastic models permit to take into account two mechanisms of randomness. The first one is connected with the random movement of the particles in the space. The second one describes random processes of splitting and death of particles. Therefore, branching random walks can be considered as a generalization of both branching processes and random walks, which are classical objects of probability theory. There is a variety of proposed branching random walks models, employing different types of branching and walking in different combinations. The important contribution to this research domain were made by Albiverio, Biggins, Bogachev, Comets, Carmona, Logal, Den Hollander, Hu, Lifshitz, Menshikov, Molchanov, Popov, Shi, Topchi, Vatutin, Yarovaya, Zituni, and others. Stress that new models of branching random walks arise not only due to mathematical interest, but also due to various applications. In this regard, we refer to population dynamics, statistical physics, chemical kinetics, and etc. The goal of our studies was the complete picture describing the evolution in space of any dimension d and time of the cloud of particles. In our previous publications, we concentrated on models of catalytic branching random walk. Namely, there was an arbitrary finite subset of the D of sources of catalysis or of branching, and we were interested in the spread of population front. More precisely, we studied the limit behavior of the appropriately normalized random cloud of particles in the sense of convergence with probability 1. It turned out that the shape of the limiting set depends on the tails of the distribution of a jump of the random walk. For this purpose, we introduced a new classification of catalytic branching random walks by means of the Perron root of a specified matrix. In our papers, it was demonstrated that new effects arise for catalytic branching random walk which do not place for non-catalytic branching random walk. You can see papers by Lally, Shaun, Neumann, Zheng. It is interesting that we propose two effective methods of finding the limiting shape of the population front. Moreover, this set P can be convex or not for different models. We also investigated the convergence rate of the normalized random set of particles to P. So earlier we were interested in catalytic branching processes and catalytic branching random walks, and we investigated the spread of cloud of particles in space with growing time. So you can see that we consider other problems different from those ones considered by Professor Yarovaya. It is worth to emphasize that the almost sure analysis of the population spread is non-trivial even for d equal to 1. We mentioned in passing that we solved the problem posed in 2020 by academician Shuraev concerning the first time when the population attains the moving boundary. Now we will discuss our new results established for branching random walk when the number of sources of branching is infinite and has the periodical structure. For such a model, at the first time, we describe the propagation of the population front with probability 1. Thus, we can compare the models with finite and infinite number of branching sources. So, as said earlier Professor Yarovaya, we are interested in branching random walk with periodic branching sources introduced in paper by Platonova and Rudolfkin in 2017. It was proposed as an extension of branching random walk with finitely many branching sources, considered in a lot of papers, example, Albiverio, Bogachev, Yarovaya, Hutu, Topcheva, Tutin, Molchanov, Yarovaya, Dorn, Roberts, Carmona, Hu, Yarovaya, Ritova, Bulinskaya, Ronville, Yu, and others. Now we give description of branching random walk with periodic branching sources. Branching random walk with periodic branching sources is a probabilistic model of the particles' population evolution due to offspring production and movement on integer lattice ZD. There are two mechanisms governing the branching random walk with periodic branching sources: walking on ZD and branching at the set gamma of branching sources. The set gamma is infinite and has a periodical structure. Walking. The walking is specified by continuous time Markov chain with the infinitesimal matrix A. A is a transition, A of xy is a transition intensity of Markov chain S from state X to state Y. We assume that matrix A is conservative, so these relations are valid, and Markov chain S is irreducible. It means that random walk S can transfer from any point of ZD to any other point with positive probability. We consider homogeneous random walk. So the intensities do not depend on shifts of X and Y. The set gamma or sources of particles branching and death is given by this formula. You see here G1 and so on. GD are the set of linear independent vectors in ZD. And any point of ZD which is a linear combinations of these vectors belongs to gamma. It is a lattice, and the set GJ will be called a basis of lattice gamma. Note that different bases can lead to the same lattice. We assume that the particles may produce offspring and then instantly die at the points of the lattice gamma only. So gamma is the set of branching sources. The branching mechanism is determined by infinitesimal generating function. It means that the probability of a transformation of a particle into k particles for time t is given by this formula. T tends to 0. Bk is the intensity of splitting a particle into k particles. K can be equal to 0, then it corresponds to death of the parent particle. Let us summarize the model description. If starting point x of the initial particle does not belong to lattice gamma, the parent particle performs a random walk according to Markov chain S until the first hitting set gamma at some point y. At point y, with the specified intensities, the particle may either leave the point and continue to perform the random walk until the next hitting gamma, or the particle may produce k offspring located at point y and then instantly die. The new particles behave themselves in the same manner independently of each other and of the parent particle. In contrast to the work by Platonov and Rudovkin, where the asymptotic expansion for the mean local particles numbers in branching random walk with periodic branching sources was obtained as time tends to infinity, we pose and solve another problem concerning the rate of the spread of the particles cloud on the lattice with respect to growing time. Spread of the particles on the lattice. The mentioned authors employ the spectral theory of operators. So they employed functional analysis, and for this reason assumed that the random walk S is symmetric. We use other methods and allow the random walk to be non-symmetric and, for example, to have a drift. Assumptions. We assume that the branching regime is supercritical. It means that the mean number of offsprings of a particle is finite and it is greater than 0. The jumps of the random walk have light tails. It means that the Cramér condition is satisfied, and for all theta from some neighborhood of 0, this relation is valid, where y is a jump of the random walk S. So the distribution of the jump of the random walk S has light tails. The Cramér condition for it is satisfied. Note that other branching regimes are not of interest from the viewpoint of the prose problem. Indeed, critical and subcritical branching random walks degenerate with probability 1, and in these cases, the problem on the spread of the population becomes meaningless. Denote by NT a random set of particles in branching random walk existing on the lattice at time t, and by xv of t, the position of particles v from set n of t at time t. Introduce also event S such that the population does not degenerate on it. It is an event on which the population survives. The probability of such event is greater than 0 due to supercritical regime. Let P of t be normalized by t positions of particles existing on the lattice at time t. So we take the random cloud of particles and divide by t the position that, and we divide by t the position of every particle at time t. So we get a random set in Rd, which of course changes with growing time. And we would like to study the structure of the set PT to find some regularity in this set. Recall the definition of the Hausdorff distance. For sets DF in Rd, the Hausdorff distance between them is specified by formula, by this formula. D epsilon is something like epsilon neighborhood of set D, and we find the smallest epsilon such that D is contained in neighborhood of F and of radius epsilon, and F is contained in epsilon neighborhood of D. So you can see here an illustrating picture the sets D and F. D epsilon 2 is a neighborhood of D, and F epsilon 1 is a neighborhood of F. And we see that epsilon 2 is smaller than epsilon 1. So in this case, the Hausdorff distance between sets D and F is equal to epsilon 1. So you see here an alternative representation for Hausdorff distance. Then our main result. Let the above assumptions, so supercriticality and light tails of a jump of the random walk, be true for the branching random walk with periodic branching sources. Then there exists a compact and convex set P such that the Hausdorff distance between our random normalized cloud of particles and P, this compact and convex set P, tends to 0 almost surely on event S, on this event when the population survives as T tends to infinity. So it means that we find the limit of the set of the random set PT, and this limit is set P. It follows from the main result that P is the asymptotic shape of the branching random walk with periodic branching sources. the boundary of set P can be naturally called the limit shape of the propagation front of the branch random walk. So propagation front of the branch random walk is moving with growing time, but its limit shape is the boundary of set P. The explicit formula for P is derived within the theorem proof. So we find this set. To provide it, we introduce an auxiliary function, function M. And you see here many new notations. For example, tau gamma 0. This is the time of the first hitting set gamma by a particle performing the random walk S. So we consider random walk. We temporarily consider random walk only, and tau gamma 0 is the time of the first hitting set gamma by particle performing the random walk. Similarly, tau gamma 1 is the time of its first return to gamma, first hitting and first return. And these Markov moments are here and here. And here. And obviously, we understand that S of tau gamma 0 is the point of set gamma which was heated, which was firstly heated by a particle performing the random walk S. And S of tau gamma 1 is the point at which the random walk returns to gamma. It is not trivial to show that this function is well defined, so it is finite, and one of our lemma is devoted to this. The formula for P is the following. So we include in the limit shape of the shape of the population in branch random walk, all Z in RD such that this set depending on Z contains this set depending on Z. Theta 1 of Z is the set in RD which is specified by this formula. But theta 2 of Z is the set when this function is well defined, is the domain of possible values of variable theta, such that the non-negative function m is correctly defined for the fixed variable z. Okay. And now we say a few words about methods of study. The periodicity of set gamma allows us to reduce the analysis of the particles cloud in the branching random walk with periodic branching to fundamental results by Biggins, proved for general branching random walk. General branching random walk is a model. It doesn't mean that it is the most general branching random walk which exists in the world, but it is a name of such model, general branching random walk. General branching random walk is specified by triple Z, M, and he, whose components describe the reproduction, Z describes the reproduction, M describes movement, and he describes importance, respectively, of a typical individual. Importance of a typical individual. Z is a point process on RD and R plus, with each point corresponding to a child. The first D coordinates give the child's displacement from its parent's birth position, and the second gives the parent age at the moment birth of a child. Here you can see some formulas from our proof of our results. They are quite. I'm sorry, but I cannot understand.
Yes, I think you.
Okay, there are.
On the previous slide, there was 3 random variables, Z, M, chi. Z was explained, but what is M and chi?
M is describes movement. So for in our so it's a process like branch, like a Brownian motion or random walk. So it describes movement of a particle. In our case, it is a random walk, and he is a contribution of a particle into a contribution of a particles when we count the population. So he indicates whether we count, namely this particle when we count the population or not. For example, we can count population only in age from 0 to 20 years, for example, or from 20 years to 40 years. So he allows to count different subpopulations in a whole population.
Thank you.
Welcome. So, example.
Ekaterina, sorry, you have say 3-4 minutes.
Okay. Yes. So, example, you see periods in red circles, branching sources, and so they are located periodically, and under other assumptions, which we omit because of lack of time, you can see this limiting shape of the front for branching random walk with such periodic structure. When the branching sources are located in this manner, you can see another asymptotic shape of the population. In a three-dimensional case, it is not a ball. It reminds us a ball, but it isn't. But its mathematical formula is not as for a ball, and this another limiting shape of the population. And conclusion. To describe the asymptotic behavior of branching random walk with periodic sources of branching, we employ the technique of Markov chains, the Laplace and Legendre transformations, and deep results of the theory of general branching random walk as well. In our previous papers, we used various tools such as multidimensional renewal of theorems, spinal technique, mainly to one lemma, construction of auxiliary Bellman-Harris branching process with many types of particles, convex analysis, martingale change of measure, heating times under taboo, determinants theorem, Tauberon theorems, large deviation theory, and coupling method. And here you can see a list of our papers on analysis of the population evolution published in 2013-2023 after obtaining the PhD degree. Thank you for your attention.
Thank you. Давайте один вопрос четко, потому что другие тоже хотят задать. Да.
А вот каталитик и нон-каталитик, что это значит?
Catalytic, it means that there are several sources of branching where the catalysts are located. But non-catalytic, it's an ordinary branching random walk. For example, a particle produces offsprings according to a point process on their lattice, and each of offsprings also produces its offspring according to the same point process, but shifted to the locations of the daughter particle. So there is no dependence on the point at which the particle is located. But when we consider catalytic or with finitely or with sources of branching random walks, it is important where the particle is located. It can be noted on. It can be not at the source of branching, and that's why it does not produce any offspring.
Thank you. May I ask also a question? I would like to know, you gave very beautiful results on this spread, and according to your study, the spread is linear in time. So my question is, do you also study the measure inside of this volume, how the density of particles? So in the previous talk, for example, in Elena Yarovay's talk, there was also on the density of particles. So do you have any information how the density distributed within this P volume?
Yes, it's a good question. No, I have no such results, but it's important that our results is approved in the sense of the most strong convergence with probability 1. So, but inside this volume, I haven't got, I haven't investigated.
And another question, sorry, I'll allow myself to ask.
У меня такой вопрос. У меня такой вопрос.
Там еще есть вопрос. Давайте.
Да. Катя, вы предполагали, что цепи всегда консервативные. Ну, то есть сумма интенсивности там равна нулю. А если это не так, что вы можете сказать?
Тоже хороший вопрос. Надо подумать.
Понимаете, там же могут быть такие мгновенные состояния.
Я понимаю, да.
И это будет накладывать существенное ограничение. Вообще это надо посмотреть.
Спасибо за вопрос, я поняла. Пока
А вот еще один вопрос тоже относится, ну, поскольку вы Молчанова тоже упоминали, если смотреть флуктуации на границе, вот у вас скейлинг вы делите на Т. А если вы на границе рассматриваете флуктуации, ну, именно границы?
Да, я рассматривала, у меня этому статья большая посвящена, ну, там 20 с лишним страниц в теории вероятностей. о скорости сходимости. И вот в случае с легкими хвостами там получилось...
Мгм.
Ага, уже
Хорошо, спасибо большое. Я думаю, что нам надо переходить к следующему докладу,
Да.
а дискуссии мы отнесем потом. Спасибо большое.
Спасибо за вопросы.